Hello and welcome back to the N25 IB Chemistry TZ3 exam walkthrough. If you're looking for the rest of the videos, they're in this playlist here. Otherwise, we're just going to be doing questions number 26 through 30 in this video. Still going in steps of 5. We're halfway there for HL, that HL exam. So going with number 26, this is a classic kinetics problem where we have a two-step mechanism. And so it's asking for the rate equation. The rate equation is going to be based on the rate limiting step. And the rate limiting step is going to be the slow step of the mechanism. Okay. And so it's not going to be based on the products. It's going to be based on the concentration of the reactants. So we can go ahead and write that rate. It's going to be equal to K, our rate constant, multiplied by the concentration of our reactants raised to their coefficients, which in this case, everything is 1. So it's just going to be the concentration of NOBr2 and NO. Okay, and so you may notice this does not match any of the freaking answer choices, which is good. I'm not going to lie, if I were making this exam, I would have made this a distractor. Anyways, and so we have that this NOBr2 is in the products of the fast step, but the reactants of the slow step. This means it's an intermediate, okay? And so an intermediate, you don't want to have its concentration in the rate equation. You want to replace it because this is an equilibrium. And so we can write out actually the equilibrium equation, the big K. So we have big K is going to be equal to the concentration of NOBr2 divided by the concentration of bromine and that NO. Okay, and so we can rearrange this to find the concentration of NOBr2 and then replace it in our rate equation. Okay, so we have over here, we can then solve for that. So we have that our NOBr2 concentration is going to be equal to big K times Br2 NO. And so we can now replace that into our rate equation. So now we have rate is going to be equal to little k times big K times our NO times our Br2 times NO. And so then if we now simplify this, these both are going to be constants. So we can just combine it into one K value as the one that we would actually observe. So this should be the rate. It's just going to be equal to K. Since they are two constants, they are the same. They don't change. Then that's why we can combine these two, if that makes sense. Meanwhile, we have NO. We have it twice. So we would have NO squared times Br2, leading the answer to this to be that nice B for that number 26. Every time you see an intermediate, you should expect to see an equilibrium that you can then replace that intermediate concentration with. Very classic two-step mechanism rate equation problem. They ask it very frequently, so be familiar with it. Moving on to this question number 27. This question is about catalysts, and so it's about which one is correct. And so for each one, we do want to either say it's correct or incorrect, and if it's not correct, we do want to justify why, rather than just saying, nah, it's not. Okay, so A, it's saying that catalysts increase the kinetic energy of the reacting particles. The only thing that's going to affect the kinetic energy is going to be the temperature, and since temperature is not affected with a catalyst, unless you're doing that in addition to the catalyst, but just a catalyst alone, not going to be affecting the temperature, then it's not going to affect the kinetic energy of the reacting particles. It is going to affect the activation energy of the reaction. It does do that, but it does not affect the kinetic energy of the reacting particles themselves. Okay, so B, catalysts affect endothermic reactions more than exothermic reactions. And so this question is kind of inadvertently asking whether or not a catalyst affects the delta H of the reaction, because that is what determines whether something is endothermic or exothermic. And so this is, once again, another misconception, is this does not affect the delta H of the reaction. The only thing it affects is does not affect the delta H, but it does affect the activation energy. Okay, and so if you have like your boop, boop, it's not affecting this part. So I'm just going to put like an X through there, but it does affect this part, and that is the same regardless of if it is. So EA, yes, but it does not affect this delta H for either type of reaction. So it does not have a strict preference it's going to have the same effect either way. For both an endothermic and an exothermic reaction, it still is going to lower the activation energy and increase the rate of the reaction. It's going to react. It's going to be doing the same thing. Okay, and so C, catalysts increase reaction rate and are used up in a reaction. So it does increase reaction rate. That part is true. However, they are not used up in a reaction and are used up. Used up essentially would mean that it would be a reactant, and then that would be it in a mechanism. It would only be a reactant and it would be used up in order to produce the product. And so catalysts, like if you were looking at something like this type of mechanism above, so an intermediate is like where it's in the products and then it's in the reactants in the next step. For a catalyst, it's kind of similar, is where it would be reactant in one step. So in the beginning, it would be a reactant, but by the end of the reaction in some other step, it would be regenerated. So it would go in and it would come out so that it can continue to go back into the circle. So it's going in, it's coming out, it's being regenerated so that it can keep doing its thing and increasing the reaction rate. Okay, and so are regenerated. And I noticed they've been asking about this a lot recently. They had a question about this, I believe, in the May exams, where they had asked about kind of a physical observation of a catalyst. And so that would be of how you would be able to separate the catalyst back out. If it was like a solid catalyst, you would not see it being like the mass would not decrease. If you had a solid catalyst, it would stay the same because it is regenerated throughout the reaction. And so C, that one would not be correct because of that second half not being true. And D, catalysts alter the mechanism of reaction. This one is true. The whole way that they end up reducing the activation energy is essentially because you have an alternate pathway. So alternate pathway. Okay. And so for that reason, D is going to be correct for this one. Moving on to this number 28, we have a classic Gibbs free energy change using the equilibrium constant. The big thing here that you want to know before we even get into it is units. Every time we're dealing with Gibbs free energy, 90% of the time there's going to be something with units that students are going to make mistakes on. So for any problem, I always recommend writing them out anyways, but for any problem, if you're going to do it, Gibbs free energy is going to be one of them. So the first thing we should note is that our Gibbs free energy change, we need it to be in kilojoules per mole. Our R is in joules. So when we do our baseline calculation, it's going to be in joules per mole initially, and we're going to need to then do another step to convert it. And you can tell this as well because in our answer choices, we have big numbers and we have small numbers. That means that they have one that is deliberately a distractor that is in joules per mole, most likely. Okay. The other thing is that we have our temperature in Celsius. Our molar, our gas constant is going to be in Kelvin. Therefore, we need this to be in Kelvin as well. And so if we just add 273.15, we do end up getting that this is 303.15 Kelvin, and then we can just directly plug it in. But we want to write out our numbers, right? So we have delta G going to be equal to negative 8.31 joules Kelvin moles. And then we have our temperature, 303.15 Kelvin. And then we have ln RK, which is that 40.2. Okay, don't be like me. When I first did this, I was having a stroke, and I was like, wait, why is this not working? It's because it's ln 40.2. It's the natural log. It's not just times 40.2. Okay, anyways. And so in this case, we're going to once again check our units. So our kelvins are going to cancel out, giving us our answer in joules per mole. And so we're just going to put that in our calculator, negative 8.31 times 303.15. And then we're going to times it by what's it called? ln 40.2. Boop. And so that's going to give us 9,305.5. And that's going to be joules per mole. To then convert it to kilojoules, we just need to move our decimal point 3 places to the left. And so that's going to be negative. There we go. So that's going to be negative 9.30 kilojoules per mole, making this answer C for that number 28. Make sure and check your units. Important. Going on to this question number 29, we are given an equilibrium. We have some starting amounts that are mixed together, and it's allowed to reach equilibrium, and then we have an equilibrium constant. Okay, and so we have a bunch of relationships about which one is true, about the concentrations of various types of reactants, products, so on and so forth. Okay, and so they have asked this type of question before. And in addition, this question was asked to SL as well. And so immediately, although you may want to make a nice table, you don't have to. And if we're going to be honest, that's just a lot of work for a paper 1A question. So we're not going to do that. Instead, we're going to look at this equilibrium constant immediately. So this equilibrium constant is 6.5 times 10 to the fourth. Or in other words, a big freaking number. Okay? And so the equilibrium constant is going to be based on the concentration of the products over the concentration of the reactants. So in general, we can also rewrite our equilibrium constant K as our NOCl squared divided by NO squared times Cl2. Okay, so we can rewrite it like that. But in other words, it's the equal concentration of the products, concentration of the reactants. And so if you have a big equilibrium constant, that essentially means that you have some combination that is equaling a big number. And so I always do this in my head is I don't have this memorized. I go, okay, if I have a big number, that means that I have to have a big number divided by a small number. And just because I'm paranoid in my head is I literally would go into my calculator and just to like verify that I'm not like having a stroke with math. And I literally would go, okay, 10,000 and I'll just add a bunch of zeros divided by 0.000001. And that gives me a really big number. And so that's verifying my conclusions there. And making sure I'm not having a stroke. Because once again, I don't memorize this. Okay, so I derive this every single time in my head. So big, small number. Essentially, all this is freaking telling me is that the concentration of my products is bigger than the concentration of my reactants. That's basically all it's saying. Okay? And so if I look at my answer choices, I'm literally just going to look for the one that's basically saying that there is some product that is greater than some reactant. Okay? And so like with A and B, those are all equals to. That requires too much math. I mean, if none of these options had products greater than reactants, then I would go and see if I could do a nice table. But I'm going to see first if I can do it without it. Because maybe I don't need to. Hopefully I don't need to. It's a 1A question. Okay? So C, we have NOCl greater than NO. Or, in other words, a product greater than a reactant. That matches exactly what we just said from our big equilibrium constant. D is the opposite, saying that we have more reactants than products. That would be if we had a small equilibrium constant. So to get a small number, you would have to do a small number divided by a big number to get a small number. And once again, you can verify that with fake numbers. And so, boom. And that is why 29 is going to be C. No math needed. Next, we have this number 30, which is another equilibrium question, but this time it's actually going to be an HL one because we have this equilibrium reaction. We have a K being 2.5 under certain conditions. We're very vague about this. And then we have at the same temperature and pressure, the mixture has these certain concentrations. And so immediately the first thing that I'm noting is that it's at the same temperature. The only thing that affects the equilibrium constant is going to be temperature. And so if we have the same temperature, that means that if these concentrations, if they're at equilibrium, they should end up equaling the same equilibrium constant because it's the same temperature. Okay? And so we can actually make our equilibrium K expression. So K is going to be equal to our concentration of this products over our reactants to their coefficients. Okay, and so we can then plug in these ones. And so this is just at a different concentrations. This essentially is inherently going to be Q that we are calculating. So we're calculating Q essentially. So because it's at these different conditions. And so we're just going to plug in our numbers. We have 0.32 divided by 0.4 squared times 0.2. And I can't do math in my head, so we're going to do this in our calculator. So we have 0.32 divided by, parentheses, 0.2 times, let's see, 0.4 squared. Boop. This is my phone calculator, by the way. And so that's giving me 10. Okay? And so 10 is not 2.5, which means that this reaction is not going to be at equilibrium. Okay? And B is forward and reverse reactions are at the same rate. That is just another freaking way to describe equilibrium. Not it. So we have C and D. And so we have at this 10, at this certain point, is we have a much bigger equilibrium constant than needed. Okay? So that means at Q, we have is obviously both of them are bigger numbers. They're both bigger than 1. So both of them have a degree of having the products being greater than the reactants, right? However, at this Q, whenever that Q is going to be 10, we need to get it down to 2.5. And so to make it become lower is we essentially need is that right now our products are much bigger than they need to be. We need to have our products decreasing. Okay, so we need some more reactants in order to make it go back down to being 2.5. Okay, just based on mathematically how that expression works. Okay, and so in order to have our products decrease, is we need to have more of that reverse rate happening. Okay, and so in order to reestablish equilibrium from our Q to make it match that K, we need to decrease our number of products. So decrease our products, which would be increasing the reverse rate to reach our K from Q, where we are at currently. And so that makes D being the correct answer for this number 30.